Okay, we take our function f of xy equals 0.04 x squared plus 0.01 y squared, and we're going to translate the thing in the horizontal, in the x and y directions by putting in a plus 0.1x minus 0.1 y. And that's going to shift the graph a little bit, and that's why, of course, our critical point came out where it did. Okay, x is cosine t, y is sine t now. So x is in turn a function of t. F is a function of x and y. X is a function of t, and y is a function of t. This means that if t changes by a little bit, that creates a change in x proportional to the negative sine of t, to the derivative of the cosine of t, which drives a change in these two terms. And if t changes by that same little bit, y is going to change proportional to the cosine of t, the derivative of the sine of t, and that change in y is going to make a change due to the y squared and the 0.1y terms. So, if we want to know how the function f changes with respect to t, the function f of x of t, y of t now, okay, the derivative of that function with respect to t is going to be fx, which is the rate at which a change in x changes the function f, multiplied by dx dt, which is the rate at which a change in t changes the value of x. And similarly, we have fy, which is the rate at which y changes the value of x. And then the dy dt, which is the rate at which a change in t changes the value of y. This then is equal and easily calculated. Fx is equal to 0.08x plus 0.1. Fy is equal to 0.02y minus 0.1, very straightforward. And then this is going to be multiplied by dx dt. X is a cosine of t, dx dt is negative sine of t. And dy dt here is cosine of t. So here's our expression for the derivative of f with respect to t in terms of x and t. Okay, the 0.34, 3 comma 4, x is 3, so 0.08x is 0.24, we add 0.1, we get 0.34. Another coincidence, we've got 3, 4 here and 3, 4 here, but one has nothing to do with the other. And then if y is 4, 0.02y minus 0.1 is negative 0.02, and that's multiplied by the derivative of y with respect to t, the cosine of t. And then it appears that I wrote it again. Not sure why. Yeah, okay, I brought this minus sign out here. That's the difference. In any case, our derivative of f with respect to t, and I wrote that as a partial, but it's not a partial. df dt, it's not a partial because there's only one ultimate variable here. Now if this is a function of t and that was a function of u or whatever, there might be two variables and we'd have partials with respect to u and v. But there's only one variable, t, so there it is. And x being a function of t, we can write it as x, and we can write y as y, or we can write x as cosine t, write y as sine t. Whichever form, this form or this form, works best for us in the situation we're in, that's the form we're going to use. Then we can simplify, if we put it in this form, we can simplify this. We can multiply the 0.08 cosine t by sine t, and the 0.02 sine t by cosine t. And I think I've got something wrong with my signs because I'm not sure that number is right. We have a negative of this and a negative of that. So let me check my signs here. 0.08 plus 0.1 sine t. It's negative because the derivative of this cosine is negative sine. And then it's plus 0.2. Okay, that's plus. That's minus. So this result is actually wrong. I have negative 0.08 cosine t sine t here, plus 0.02 sine t cosine t here, which leaves me negative 0.06 sine t cosine t. And then I have a negative 0.1 sine t and a negative 0.1 cosine t, and that works out. We have a negative 0.1 times sine t plus cosine t. Okay, well that's just arithmetic. It's just simple algebra. You just got to get it straight. The process and the essence of it is simply that the derivative of f with respect to t is fx dx dt, fy dy dt, and try to understand that in terms of a change in t changes x, and a change in x changes f. Change in y changes t, a change in t changes y, and a change in y changes f, at the rates are indicated here. Okay. Now I want to consider a little bit more about saddle points. I'm going to take the function f of xy, the 0.04 x squared plus 0.01 y squared, and I'm going to add 0.1 xy. Now the graph of z equals 0.1 xy then would be added to the graph of z equals 0.04 x squared plus 0.01 y squared. The graph of this function we know is the elliptical paraboloid. The graph of this function, well, let's analyze it a little bit, and just in a straightforward manner. If x is 0, that makes z 0. If y is 0, that makes z 0. So x and y axes are part of the surface. So whatever the graph of the surface looks like, when it gets to the x and the y axes, it incorporates the whole x-axis and the whole y-axis. Now I'm looking at the figures, something I thought about doing, but I'm not going to. Okay. If x equals y, we get z equal x squared. Well, here we have a coordinate, a three-dimensional coordinate system, and we have a line here down in the xy plane at 45 degrees with respect to the y or the x-axis. Okay, so if x is here, y is here, and z is here, this plane is in the xy plane, or this 45 degree line is in the xy plane, and we're going to cut the surface this way. And when we do, the value of z is going to be equal to the value of x squared. Also to the value of y squared, since x equals y. But that's going to give us a parabola, an upward opening parabola above this line. It's going to be like this in this plane, and above this line at 45 degrees to the x-axis. If x equals negative y, we get z equals negative x squared. Because, of course, I was a little careless when I wrote this. Z should be 0.1 x squared, and here it should be negative 0.1 x squared, because you have the 0.1 there. Again, so if x equals negative y, then we substitute negative x for y, and we get x times negative x. 0.1 times x times negative x, negative 0.1 x squared. Okay, now that means, well, x equals negative y is the 45 degree angle here. Perpendicular to this line, we have the line where x equals negative y, and now we have a downward opening parabola, negative 0.1 x squared. So we have a downward opening parabola above or below this line. I'm afraid to do too much shading. And an upward parabola here above this line. Opens upward this way, opens downward this way, and it coincides with the x-axis and the y-axis. We try to visualize that. Point is, this thing doesn't have a maximum or a minimum. This curve has a minimum at the origin, this curve has a maximum at the origin. So the origin, which is going to be a critical point for this function, actually it won't be the origin, but actually, yeah, no, I take it back, it will be. It's going to be a critical point, but you have the function going this way in one direction and this way in the other direction. You have what's called a saddle point. Okay, now showing that that's the case, we can do the discriminant test that we've seen earlier. If f of xy is 0.04 x squared plus 0.01 y squared plus 0.1 xy, the function we have here. For saddle point at the critical point 0, 0, and you can verify 0, 0 is a critical point, this discriminant is fxx, fyy, minus fxy squared. And I commented at this point that this is two second derivatives multiplied together. So it's like a squared second derivative, but two different second derivatives. This is a squared second derivative of the fxy. So it's like you've got two second derivatives multiplied together here, fxy with itself, and two second derivatives multiplied here. So you don't want to forget that, because you don't want to write this down as just fxy. You need two terms here, just like you have two terms here. Two factors here, just like you have two factors here. Okay, well, in any case, fxx and fyy are 0.08 and 0.02. fxy is 0.1. We do this, we get 0.0016. We square 0.1, we get 0.01, and that's less than 0. That's negative 0.0084. So we have a saddle point. I also write a note that if the function, instead of having a 0.1 in front of xy, had a 0.04 in front of xy, this quantity would be 0, because the fxy would be 0.04, and the square of 0.04 is 0.0016, so you'd have 0.0016 minus 0.0016, and you can work that out yourself. So if f of xy was this, the discriminant would be 0, so the test would be inconclusive. Okay? Going back to the picture of adding the graph of the 0.1 xy function, which has its saddle point, to the graph of the parabolic, or the elliptical paraboloid. If the elliptical paraboloid goes up fast enough, it can overcome the tendency of the 0.1 xy function to be concave down in this direction. But if this function has too big of a coefficient, that doesn't work. Okay, if the coefficient's 0.1, you see that we get a saddle point. If the coefficient is a little smaller, 0.04, and you work it out, you're going to get 0, and you don't know if you have a minimum at that point or not until you do some other tests. If that coefficient was 0.03, then the discriminant would be positive. And the steepness of the elliptical paraboloid would exceed the steepness of the descent in this direction, and you would have a minimum at the point 0, 0. So that's worth thinking about.